In this video, we're going to look at another example of work integrals. A leaky bucket with mass 12 kilograms is raised from the ground level to a height of 10 meters at a constant speed with a rope that has linear density of 3 kilograms per meter. Initially, the bucket contains 40 kilograms of water, but the water leaks out of the bucket at a constant rate and finishes draining just as the bucket reaches a height of 10 meters. That means the mass of the water in the bucket is 0 kilograms as the bucket reaches the top. Find the work done in raising the leaky bucket to a height of 10 meters. There are three components here that we have to look at, and then we're going to add up these three components of work, that is. So work done to lift the empty bucket, dy meters. Work done to lift a piece of rope, dy meters. And work done to lift leaking water, dy meters. All right, here we have a diagram. So we have the leaky bucket at the bottom, and it has to be lifted 10 meters up. So the rope linear density is 3 kilograms per meter, and gravity G is 9.8 meters per second squared. The mass of the empty bucket is 12 kilograms. The mass of water at ground level is 40 kilograms. So we have 40 kilograms of water inside the bucket when the bucket is at ground level. And the mass of the bucket the mass of the water at the top level at 10 meters is 0 kilograms. And now look at the segment of the rope here. You can see that this segment of rope is y units from the bottom, and hence it has to be lifted 10 minus y meters. It has to be lifted this segment of the rope has to be lifted 10 minus y meters to reach the top. All right, so first let's look at the work required to lift the bucket 10 meters to the top. Well, the mass of the bucket is 12 kilograms. Work is equal to force times distance. The force is equal to 12 kilograms mass times gravity, 9.8 meters per second squared. And that gives us 117.6 newtons. And work is equal to force times distance, so that's going to be 12 times 9.8 times 10. Multiply all of this out, we get 1176 joules. This is the work done to lift the bucket 10 meters to the top. We can certainly set up an integral, a definite integral as well. We just integrate from 0 to 10, 12 times 9.8 dy. And that would also give us the work. All right, so now let's look at the work done to lift the entire rope 10 meters to the top. So a piece of rope of length dy, let me fix this here, length dy and dy meters at height y meters from the ground level has mass 3 dy. So differential mass is equal to 3 dy. This is the mass of the rope in the segment y plus dy. In this segment here, this is the mass of rope basically. All right, now the key idea is that this piece of rope has to be lifted 10 minus y meters. And the reason is because this piece of rope is y units from ground level. So the distance that this piece of rope, this segment, has to travel to reach the top is 10 minus y meters. Very important. All right, so now dm, differential mass, the mass of this small piece of rope is the density 3 times dy times the length of the rope. dF, differential force, the force of gravity acting on this piece of cable or piece of rope, same thing, 3 times 9.8 times dy. This is a force of gravity acting on this piece of rope. dW is equal to 10 minus y times dF. This 10 minus y is the distance that each segment of the rope has to travel to reach the top. And from the diagram, this is 10 minus y here. This is a distance 10 minus y that each segment has to travel to reach the top. All right, so dW is equal to 10 minus y times differential force, which is 3 times 9.8 dy. This is the work required to lift a small piece of rope 10 minus y meters. Now let's integrate and add up all those segments. Add up the work required to lift every segment to the top, every segment of the rope. Y equals 0 to y equals 10. We integrate dW. So we get the definite integral, 0 to 10. 3 times 9.8 times 10 minus y dy. Density of the rope, gravity, and distance. Force times distance. Now, let's find the total work required to lift the entire rope. So we're going to, this is 3 times 9.8 is a constant, passes through the integral. So we get 3 times 9.8, integral 10 minus y dy, integrating from 0 to 10. And we reverse the power rule, so 3 times 9.8. Let's integrate 10 minus y. What is the antiderivative of 10? That's just 10y, because integral of 1 dy, integral of 1 dy is equal to y plus c. What is the antiderivative of y? That's y squared divided by 2, evaluated from 0 to 10. 3 times 9.8, that's 29.4. Put the upper limit in, we get 100. Minus 10 squared, 100 over 250, minus 0. If we put this into a calculator, we get 1,470 joules of work required to lift the entire rope 10 meters. So just to backtrack, just to review, we found the work required to lift the bucket, the empty bucket, 10 meters to the top. We also found the work done to lift the entire rope 10 meters to the top, and we did that through integration by finding the work required to lift each piece of the rope 10 minus y meters, and then we used an integral to sum up all those works that's required to lift up the entire rope. Now, lastly, we have to find the work required to lift the 40 kilograms of leaking water to the top. This part is a little bit harder. The key concept is, since 40 kilograms of water is leaking at a constant rate from ground level, y equals 0, to the top level, y equals 10 meters, we must express mass of water as a linear function of the height y. That is, we have to find mass as a function of y. So let's do that. When y equals 0, when the bucket is at ground level, the mass of water in the bucket is 40 kilograms. When y equals 10, when the bucket of water is at top, then the mass is 0 kilograms because all the water has drained out. Setting up a linear function, you get m minus m1 is equal to delta m delta y times y minus y1. This is the point slope form for a line, kind of like y minus y1 is equal to m times x minus x1. All right, so that's just the equation of a line. Okay, so let's solve this one. We get m minus 40 is equal to, the change in mass is going to be 40 minus 0 divided by the change in distance, 0 minus 10 times y minus 0. If you simplify this, we get mass as a function of y is equal to 40 minus 4y. Does this make sense intuitively? Well, let's check it out. If y equals 0, the mass of the water should be just 40 kilograms. And if you plug m of 0, plug y equals 0 inside the mass function, we get 40 minus 0 is equal to 40. When y equals 10, the mass as a function of 10, mass of y should be 40 minus 4y, 40 minus 40 equals 0. And that makes sense as well because all the water has leaked out. So when y equals 10, the mass of water should be 0. So we now have a linear mass of water as a linear function of y. So what we have is dW is equal to 40 minus 4y, and this is mass of the water as a function of the height, times gravity, which is 9.8, times this is gravity, times distance, which is dy. So the work required is integral y equals 0 to y equals 10 dw. So we integrate from 0 to 10. These are y limits of integration. 40 minus 4y. This is, of course, the mass. Times gravity, 9.8. Integrate with respect to y. 9.8 is a constant, passes through the integral. We get work is equal to 9.8 times integral. 9.8 integral from 0 to 10. 40 minus 4y dy. So work is equal to 9.8. Integral of 40 is 40y, reversing the power rule, and integral of 4y is 4y squared. Divide by 2. Evaluate from 0 to 10. So we're just reversing the power rule. Integral x to the n dx is equal to x to the n plus 1 divide by n plus 1. Add 1 to the exponent, divide by the same, plus c. All right, so now let's put the upper limit in and lower limit, apply fundamental theorem of calculus. 40 times 10, that's 400. Minus, and 10 squared is 100 times 2, that's 200. Minus, plug 0 in, that's just 0. So we get 9.8 times 400 minus 200, that's 9.8 times 200. And we get 1960 joules. This is the work done in lifting 40 kilograms of leaking water 10 meters to the top level. All right, so now let's add up the three components of the work and find the total work required. So dW total is equal to dW empty bucket plus dW rope plus dW, let me write that better, dW water, the leaking water. So dW total is equal to 12 kilogram, it's a 12 kilogram bucket, times gravity 9.8 times dy. dW for the rope is 3 kilograms per meter, that's the linear density for the rope, times gravity 9.8 times the distance that every segment of the rope has to travel to reach the top, 10 minus y. Plus dW for the water is 9.8, gravity, times the mass of the water, 40 minus 4y, we got the mass as a function of y, times dy. And the integral adds up all of these, so work is equal to integral from 0 to 10, 12 times 9.8 dy, plus integral from 0 to 10, y equals 0 to y equals 10 meters, 3 times 9.8. This is the work required to lift up the entire rope 10 meters, 10 minus y dy, plus integral from 0 to 10, 40 minus 4y times 9.8, and let me put a dy here. So the first integral represents the total work required to lift the empty bucket 10 meters to the top. The second integral is the total work required to lift the entire rope piece by piece 10 meters to the top. The third integral is the work required to lift 40 kilograms of leaking water to the top 10 meters. So add up these works, we get 1176 joules for the work required to lift the bucket, plus 1470 joules, the work required to lift the entire rope to the top, plus 1960 joules, which is the work required to lift the 40 kilograms of leaking water. So the total work done in lifting the bucket of leaky water plus the rope 10 meters to the top level, add these all up, we get 4606 joules. This would be considered kind of an exam type question. It's a tough question, so it's the kind of question you want to go over it very thoroughly. All right, thank you.